take an existing project and save it under a new name if you want to make a copy so that you don't mess up your old project, especially if you have an upcoming write-up. You need your old project intact. The other thing is if you want to add a source from a previous project, like reuse your counter, for example, you can use add sources, and you go to, instead of create, you're going to want to add file, and then you're going to want to go find it. Okay, let's go find my counter. It's in sources. Okay, there's my 15-bit counter. I probably want to get my 5-bit counter too, by the way. But anyway, I'll say, okay, now, very important is this box here, copy sources into project. If you don't click that box, Vivado will just add a link to your 15-bit counter sitting in your Lab 3 project. Okay, you'll proceed and you'll work on your lab and it'll seem just fine until you go to zip your project. Because when you zip your project, it's only taking what's in your directory. It's not going to follow that link. It's not going to take that 15-bit counter with it. So now you have a zip file, you go open it somewhere else. You don't have that 15-bit counter with you. So make sure you click this box to actually copy any sources into your project. The other problem is, suppose I want to modify my 15-bit counter. That's a really bad idea. Suppose I want to. If I go modify that file now, and it's sitting in Lab 3, I've actually modified the source in my Lab 3 directory. Okay, and so now I've modified my only copy of the 15-bit counter if I ever needed to use it again, or if I wanted my Lab 3 might not work anymore. Okay, so you make sure you actually copy sources into your project directory, and you can do that, ensure that by paying attention to this little box here. Okay. Sometimes you already have a file in your project directory, and it's just not part of your project, and you decide, oh yeah, I do want it in my project. Then you wouldn't want to do that because it's already in there. Okay. Any questions on that? I'm not going to do this. Okay, I see that, unfortunately. People have incomplete project files because they didn't copy sources into their project directory and then zipped it up. Yes? No. You might want to fix that. Is Lab 4 submission still open? Okay. You can go back and then actually copy the source. Now, I have to say that I'm a little frustrated helping a few people on Friday that people seem to think they needed to go and fix their 5-bit counters and change them. You don't need to fix your counters. If your counters work right for Lab 3, don't fix them. Just use them as is. There's a reason we made you load them, so that you could set them to any value you wanted to. Okay. It's one of the commandments of hardware design. If it isn't broken, don't fix it. Yes, did you have a question? Hello? Did you have a question? No? Okay. Any questions? No questions. Okay, all right. Let's reclaim my memory here, because otherwise nothing's going to work right. Okay, so on this schedule, homework 4 would be due in 2 days, so that's not going to happen because I haven't even posted it yet. So actually, homework 4 won't be due till next Wednesday, but that'll give you a week to do homework 5, okay? All right. We have a holiday next Monday. Any questions before we start talking about traffic lights? Yes?
What does the progress on the midterm look like?
Oh, I was just looking at that. Okay, so midterm is 76% done. I'm guessing it'll be in a few days. It'll be done. That's the good news. Homework 3 is only at 27%. It's kind of annoying that all your readers are busy at exact time. You need them. They're all doing their own midterms and grading, doing their own assignments. Any other questions? Okay, so let's do this one. Okay, so this is the Hello World of state machines. It's probably the first basic state machine that's often used in hardware designs, in hardware design classes. And it's the traffic light controller. It's an actual state machine that you encountered in real life today. Is there a traffic light on? Yes, there is. There is a traffic light on campus. Okay. All right, so here's the basic setup. We have an intersection. We have traffic going north-south, and we have traffic going west-east. And we need to control the traffic because we want to avoid car accidents. And we notice that even though there are 4 lights, they're actually pairs of lights, right? The north-south lights will always be the same, have the same value, and the east and west facing lights will also be the same. Okay, so let's build this traffic light controller. We are going to need to control the lights and have them step through, so they're going to be on for a certain time, and then we're going to let the other direction go. And I think in the early 1900s, I think I read somewhere that a policeman in New York City decided it would be a good idea to have a yellow light in between the green and the red. So we need something we need a timer. And for that, we're going to use just a simple 3-bit counter. We could make it more sophisticated and count at a higher resolution using a faster clock. But this is simple enough. So when bit 1 goes high, that's going to tell us that the short amount of time, this is for yellow lights, has expired. And TC will be for the long lights. So we're going to want to keep each green light on for a certain amount of time. Don't want it to just go on and off real fast. Okay, so we also have lights. And as mentioned, we only really have two sets of lights to control. And each of these pairs of lights has 3 different possible values, right? They could be green, yellow, or red. And so we need actually 2 outputs for each light because we need to tell it 3 possible colors. Okay, so there's 1 value that's not being used. Okay, so our traffic state machine needs to know about the timer. So it needs to know when a short amount of time is expired and a long amount of time. It needs to provide outputs for each pair of light. And it needs to control the timer. So it needs to reset the timer whenever the light has changed. Okay. So it's going to make those connections, right? It's responsible for controlling the lights. It's very important we get this right, because if we turn on if we make both sets of lights green, this is not good. If we make both sets of lights red, that's not good either, but it's not as bad as making them both green. Yes?
Does this state machine incorporate the fact that
No,
Because I know traffic lights do that.
do they? Maybe, well, that might be an idea.
Okay, so this state machine does
This
not
one
do
does
this.
not. This one,
Alright.
this one is for Santa Cruz drivers.
Who
Okay,
are notoriously nicer than LA drivers.
chill. It's cutthroat in LA, what can I tell you? All right, so here's our traffic light controller. And the state machine basically is just going between 4 different states. Right? So if one light is green, we know the other one better be red. So I don't even actually need to specify that. So when the north-south light is green, the east one west will be red. Then after a long amount of time, we will reset the timer and go into north-south yellow. And east-west still better be red, right? And then when the small amount of time expires, then we will turn the east-west light green. And again, I know it's implicit here that the north-south had better be red at this point. And now we will, again, reset the timer. This time we wait the long time, so we're going to keep the light green for east-west a long amount of time. And after a long amount of time, we'll again reset the timer, make the east-west yellow, and then wait the short amount of time, and then again the north-south will be green. Okay, so it's pretty straightforward. We stay in one of the 4 states, and we wait the amount of time. If it's a green light, we wait a long amount of time. If it's a yellow light, just a short amount of time. Okay. What about encoding? We need to encode the colors. So again, there are 3 different colors. So we're going to use 2 bits for the light output. Most of our state machines so far have only had 1 output, and so we've only had 2 values. But here we have actually more than 2 values for the output, so we made more than 1 bit. And we will immediately encode that when the north-south is green, then the east-west had better be red. Right? So the color of the north-south being green or yellow implies that the other direction is red. And when the east-west is green or yellow, the north-south had better be red. So 0, 0 is red. Okay, so that's it. And what about a different city? Where, as was just suggested, we should not go directly from yellow to green in the other direction. Right? And in fact, I think most traffic lights are like that.
Oh, cool. So I was skipping slides.
Right?
Oops, thanks.
So let's say that we don't want immediately to, as soon as it's yellow, let the other direction go. Then what we need to do is actually be in a state there, and that's what this state diagram does. We have a gap. So for example, if we go from north-south green to north-south yellow, instead of going directly to east-west green, we go to what we call a gap. I called it a gap state where both lights are red for a very short amount of time. Okay, so that drivers who think yellow means hurry up, the light's about to turn red, hopefully will not encounter another car. Okay, so this is simple enough to do, and your state machine requires another state to wait in between. And of course, our counter now needs another output for the gap timer, maybe be 0. Again, you can customize the amount of time, just changing the length of these, the resolution of the timer, and exactly which bit you use. Okay. And again, now our states, the outputs for each of our states are pretty much the same, except for now we have the red gap state. We have two red gap states, east, west, and north, south. Now these two gap states have the same output, right? And these two gap states, all the lights are red, but they're separate states because we need to remember who gets the green light next, right? We can't merge that into one state because then we would forget which direction gets to go next. So that's remembered by the state machine, right? These two are not the same. Okay. All right, so that's one. Well, how about another variation? So not all intersections are democratic. Have you noticed that? It always seems like the other direction has a longer green light than your direction. No, it's just me.
Yes.
Yeah, okay. Well, so some of this has to do with the amount of traffic. And one thing that happens is you have a major road, artery, with a lot of traffic, and side roads with a small amount of traffic, and you would like to increase the flow or enhance the flow on the bigger road, on the main road. And one way to do that is to prioritize the main road. So you could give it a longer light, but one other thing to do is to only respond to the side roads if there's actually a car there. So don't turn the light green for a side road if there's no demand, if there's no car. And to do that, we need to add sensors. And so I'm sure you've seen this. Sensors in the road, and sometimes there's cameras doing this. And if you're riding a bike, it's highly annoying because it's hard to trigger it sometimes. You have to get off your bike and push the pedestrian to get across. But anyway, okay. So here's our sensors. So now we can tell if there's a car waiting on the side road. And the protocol that we're going to follow is the east-west will only get a green light if there's the north-south will only get a green light if there's a car waiting. But not right away, only once the main traffic light has been green on for a long amount of time. So we're not going to immediately trigger the light for north-south. We're going to let east-west go for at least T1. And then the north-south, for some reason there's a lot of traffic on the north-south. They're still out of luck. They only get the green light for a T4. So there's a maximum for T4. So here's our state machine now. So we have now an input for whether there's a car waiting, whether the sensor has detected, and it doesn't matter which sensor. Right? It doesn't matter whether it's going north or south, so we probably could OR the two and have one input. We have the long amount of time that we're going to run the east-west traffic, and we have the long amount of time that we're going to allow the north-south green to stay on. And again, we have the short amount of time for the yellows. Okay, and we have our timer and our lights again. Those didn't change. And so this one doesn't have the gap. We got rid of the gap, just to keep things simple. Okay, so now we're in north-south. And these, here your Boolean algebra really needs to be sharp. Okay, so here in the north-south, we get to stay in the north-south as long as there are cars. There are no cars. It's over. And the T4 time hasn't expired. So no more than T4, and only while there are still cars. If either time has expired or there's no car, we turn the light yellow. It's yellow for time t2, and then east-west needs to be green. Now, for east-west, we actually need two states because we need one state to guarantee that we're going to stay it up. It's going to stay on for at least time t1. So we're going to stay here for time t1. Then after t1, we're going to stay as long as there's no demand on the north-south road. So this was done with two states. Okay, and then as soon as a car wants it, then we will turn it yellow and go back to north-south green. Okay. So it's really important to get these things right. I can tell you that, you know the intersection on High Street near the Westlake Elementary? Yes. Okay. So they put a camera, about 15 years ago, they put a camera there, and they had the bright idea that if cars were coming up High Street, they would just automatically turn the light red to stop slow traffic along High Street. The problem is they weren't turning it red in both directions. Yes?
Wouldn't it be possible to combine East-West 1 and East-West 2 into one state?
So what would be your logic for staying there?
The logic would just be if it's car waiting, not car waiting, or not T1, and when it transitioned, it would just be car waiting and T1.
Car waiting and T1.
Yeah.
Well, the question is T1 going to stay high?
Yeah.
Is it?
Well,
It's
you
a,
have to reset it as well when you transition from East-West 2 to yellow.
well, we sorry, okay, it got reset here. I forgot that. Let's say it's reset here. Okay. But, this is an excellent question. So let's look at this. So this is our timer, right? We just reset it. So do you think, is this going to stay on?
After a while.
So let's say there's no cars waiting, and T1 goes off. If that timer is going to keep counting, right? And T1's going to go low again.
Oh, I see.
So you're going to miss it, right? So what would happen? What would happen is that if T1 stayed high, then what you're saying would work, but T1 won't stay high. And so if we were to combine this and say T1 and car waiting, you would have to have a car waiting possibly to hold T1 after it arrived, depending on when it arrived in the cycle.
I see.
Okay, now if you want to do that, you could arrange for T1 to go high, to stay high, maybe set a flip-flop, which in effect adds a state. So it ends up being about the same. Okay, so that's an important point. If you're looking for a condition, and that condition will not stay, you better catch it. You better immediately catch it and change state to record that you saw it. Right? Because T1 is not going to stay high. You have to capture that in your state. Okay, so where were we? I was digressing. I was talking about
The
High
High
Street,
Street.
okay.
Slowdowns with the red light.
so that whoever was in charge of the state machines had decided they were going to turn the light red, but only in one direction. So I was traveling down High Street, the light turned green. The light was green, but for the other direction, the light went from green to yellow to red, so cars started turning left right in front of me. because it naturally assumed that my light was turning red too. Oh. So, okay, you need to be extremely careful in your state machines and think about all these things. Okay, and how people are going to interact with them and how other components are going to interact with your state machine. Okay. That is a yikes. That was a yike. I actually called the traffic engineer, had a long discussion with him, and the following week it changed. So, they don't do that anymore. All right. Any questions on traffic lights? Okay. I know you're probably not going to design traffic lights, but there are a lot of situations that effectively are very similar, and they involve clients versus server interactions. Okay. So, for example, in your Lab 4 state machine, Lab 4 project, you have a state machine, and it has the LED processor. Now, your LED processor is dedicated to your state machine. It's not worried about anything else. And it will respond right away to your state machine. It's paying attention all the time to your state machine. Okay, but that's not always the case. Sometimes the component may be busy and can't respond right away. So maybe you have a client, maybe Fred, and it needs to use a resource. Okay, so Fred has to ask the resource, hey, I'd like you to do something for me. So it's going to assert that it's go output. And if the resource is also providing an output that's connected back to Fred that says, okay, yes, I'm ready, I can respond to your request. So it's going to tell Fred, okay, go ahead, send data, or use the adder, or use the multiplier, or whatever. Okay, and so you have this interaction between the client here, Fred, and the resource. Okay, now in your state machine, the LED processor doesn't need to tell you it's ready. It always ready. So not a problem. And what would Fred do? How would Fred operate? Fred, in Fred's state machine, because Fred has to have a state machine, of course, when Fred wants to do something with a resource, Fred will go into a state, I called it set up here, and it will assert go. It'll say make go high, and then it'll wait until the resource says it's ready. And once it gets that ready signal, then it'll go to another state where it will do things, whatever it needs to do. If it were just to not wait for the ready, it's possible that all of the stuff that Fred would do would not work or would not be processed correctly. Whether or not Fred needs to keep the go high, that depends on the situation. Okay. All right. So you're going to have things like this in your state machines, and for the most part, your resources are dedicated to your project, and you don't have to worry about multiple clients needing them. But in large systems, you need to control access when there are more than one client. You can't have several clients trying to use the multiplier or use the memory or use the GPU at the same time. So how do you do this? Well, you use what's called arbiters. So here's Fred again. And there's our resource. And Fred would, of course, like to use the resource, but the problem is Sally wants to use it too. Okay, we could just put an OR gate there, except then both Sally and Fred might get the go-ahead, and that might be a disaster. So we need somebody to decide who gets it, Sally or Fred, because they can't both have access at the same time. Okay, so our arbiter is essentially a state machine, and its job is to take the input from Sally and Fred and to tell one of them to go ahead. So again, we could put an OR gate here, but only one of them is going to get to use. And so only one of them will get the resource ready signal. So resource ready will come back, but because we have these AND gates here, only one of them will get back to Sally or Fred, not both. Okay, so that's the job of the arbiter, is to take in two requests and to grant to one of the two, not both. Okay, so, well, what does this look like? Well, we could do this. So we could, of course, we always start out in chill, and if no one's requesting them, we stay put. And if, let's see, Sally requests it, then Sally gets it, and Sally gets to keep it as long as Sally wants it. As soon as Sally doesn't want it, go back to chill. Or, and we could go here, if Fred wants it, we'll have a similar state over here. Okay, and Fred gets to keep it until Fred doesn't want it anymore, and then we'll go back to chill. Yes?
So in chill, not all of the transitions are defined.
They're not?
R1 and R2.
Yeah, what about R1 and R2?
What would the state machine do if both are high at the same time?
It would go to two different states and grant it to both of them, right? Depending on how we did our logic. So this is not allowed, right? Exactly what you're pointing out. Whoever designed this state machine made a terrible mistake because they have two arcs here that are not mutually exclusive. Right? If R1 and R2 are both high, both those arcs are true, and you're confusing the state machine. If it's one hot, it'll go to both states, which is a new state, if you like. If you're using some other encoding, who knows what will happen, what state you'll be in. Okay, so this if you have a state machine like this, it's not a well-defined state machine. Okay. All right, so I have decided that Sally wins. Okay, arbitrarily. So here's a version where I solve the problem, and all I need to do is change this arc that said, Fred only gets it if Sally doesn't want it. Okay, and now these four arcs are mutually exclusive. Sally gets it if Sally wants it. So this is 1, 1, and 1, 0, and this is only 0, 1, and this one is 0, 0. Okay, so we solved that problem. Okay. Sally always wins, is this solution. Is this a good solution? Not if you're Fred. If you're Sally, it's great. No. Okay, so there's a fairness issue with this, right? And sometimes you have systems where you don't want to be fair. One device should have priority, and that's fine. But if you want to be fair in your requests, you're going to need to break ties in a way that's not arbitrarily for one requester over another. So there's different approaches to this, depending on your goal. Here, we're going to say we're going to alternate who wins in a tie. Okay, so how many of you watch college basketball? No. Okay, so there is something similar in college basketball. Yes. No. What? I think I heard it. Jump balls. So in college basketball, there's a little arrow on the court, and jump balls are decided by the direction of the arrow, and every time there's a jump ball, it flips. I don't know who gets it first. Is it the home team or the visitors? I don't know how I did. Yeah, the jump. Oh, who? Okay, determined by the first one. Okay. All right. All right. So we're going to do the same thing. We're going to have to keep track of who won the tie last. Sorry, who won the tie the last time, or who had the ball, or the request the last time, and break ties accordingly. So the first tie is again going to be Sally. So Sally still has a small advantage. So Sally wins if we are in chill 1. And we'll grant it to Sally. And Fred only gets it if Sally doesn't want it, if we're in chill 1. But, we'll go directly to the other state if one of them doesn't want it anymore and the other does. So you can go directly from grant 1 to grant 2 if the other requester wants it immediately. But once Sally no longer wants it, we'll go to chill 2. Okay, so we gave it to Sally here, right? If Fred wants it right away, we'll give it to Fred. But if nobody wants it, instead of going back to chill 1, we're going to go to chill 2. And in chill 2, we break ties for Fred. So what's happening here is we're actually not alternating the winner of tires. We are breaking ties in favor of the person who didn't have it last. I should change that. Okay. Remember to change that. So whoever did not have the resource last will win the tie. So arbitrarily we'll start in chill 1. Chill 2 indicates Sally had it last. And then chill 1 indicates that Fred had it last. Or we're at the very beginning. Okay. So you can implement different policies about this according to your wishes. Yes?
Are we going to cover state machines that do this, but with an arbitrary number of people to decide between in this class?
You can expand, it's not just 2. You could do this for any number of requesters. It gets obviously very complicated. how you're going to break things up and priority schemes.
I mean, if you had an arbitrary number, you could do something like, because I took 138, so I have notes on chord. I pulled them up so I could remember how that was done.
Yeah,
But like,
whatever policy you want, but you need to do it in your state machine.
is there a certain point where you would sort of factor out knowing who comes next from being a state of its own to being an input to the state machine?
Well, then you probably have somebody keeping track of that, right? You could have a state machine whose job is to keep track of who.
Second state
No, it's another state machine, and then whether that's 2 state machines or just one big complicated state machine is a state encoding issue. But anyway, okay. The problem with this, there's still an issue here with this type of arbiter, and that is that it allows starvation. Starvation is when somebody gets to hog the resource endlessly, and while another client is starving, not getting any access to the resource at all. And for that, you need, of course, to limit access and use a timer or some other measure of how long a the client can keep a resource. Okay. Any questions on this? Yes.
Would the best solution be to start the timer when the opposite person wants it, or rather instead of having the timer be for how long the person timed it?
Yeah, you could do that. It's really the state machine captures whatever policy you want. That would work. Right, we were doing with the north-south and east-west traffic, we were guaranteeing the east-west a minimum amount of time. Right, they had at least T1. And we were capping the amount of time that the north-south had at T4. Okay. All right. So next I wanted to go over designing some state machines. Can you read that, or is it too small?
We could use a little bit of zooming.
Well, you're in the front row, Clara. Somebody in the back row. Tell me. You're okay?
Well, I said it could use a little bit of zooming, and I'm in the front row.
Okay. All right. Okay. So, if you're designing a state machine to do various tasks, one of the tasks is to look for specific patterns in an input, right? And so here's a word problem. And so I thought we would work some of these in class, because there might be some on the homework and an upcoming midterm. Okay, so they help you capture how state machines work. Okay, so this problem, we have a sequential circuit with one synchronous input and one output. Okay, that means it looks like this. One input, one output. Okay. Okay, now, what the heck does it do? This circuit output is 1 after, this is in bold, after it receives an odd length block of zeros followed by 2 ones. Okay, so a block of zeros is basically consecutive inputs that are zeros, an uninterrupted sequence of zeros. And we need 2 ones, so it has to be odd length. 1, 2, 3, 4, 5, so that's odd. That's not the only odd number, but 5 is odd. And we need 2 ones. And let's see, and the output stays 1 until after receiving the next 0 input. Oh, and then there's a helpful note here. A block of zeros is a sequence of one or more consecutive zeros preceded and followed by a 1. Okay, so we have to have a 1 here before it in order to consider this a block. Okay. Okay, so let's look at the sample input here. Okay, so this is 3 zeros and 2 ones, but there's no 1 in front. So this doesn't count. Okay, so here's another odd length block. Oh, and it has 2 ones after it. So 1 is an odd number. Here's another one, but it only has 1 1. Okay, so that didn't meet it. Then we have 1, 2, 3, 4, 5. Oh, we have 5 here. Okay. We have another one here. This is 2 zeros. That doesn't count. 2 is even. Okay. All right. And now it says the output should go high until after the next 0 input. Okay, so now notice that it said after, so it's not going to happen on this same clock edge. It's going to happen the following clock edge. So we went high here because we had a 0 and then 2 ones. And we stayed high until, after Okay, so it has to be after this 0. Okay, the next one occurred here. We go high. But this one was 0 immediately, so we went back to 0. And then, let's see, here's another one. We went high, and then we have a 0, so we went back to 0. Okay? All right. So let's design a state machine that does this. Okay, so what state should we start in? This is a hard question. Let's start. No, it's not. Okay, so we're in chill.
I was gonna say chill state, and when you said it's a hard question, I went, is the answer not chill state?
You take me seriously?
Yes.
Okay.
I'm sitting in your lecture. Of course I'm taking you seriously.
Okay, all right. I shouldn't have asked that question, but anyway. Okay, all right, what happens here? What happens in the states? Jake, what happens? No? Nothing happens because we didn't connect the clock, I know. Okay, what happens, Giovanni?
Stay in chill as if we receive zeros until we receive a 1, then we move to another.
Okay, so in order to have a block of zeros, we first have to have a 1, right? This initial block of zeros doesn't count, so we're going to eat all the zeros at the beginning. Nothing will happen with them. Okay, we got a 1. Yes. 1, okay. Okay, so we stay here when we don't have a 0, and you want me to go somewhere when I get a 0. Okay, I got a 0, okay.
A state named on.
Okay.
And if we get a 0, we go to a different state named even.
Okay.
If we get a 1, I guess we need a new state for receiving the last 2 ones.
Well, from where?
From odd.
From odd. So if I get a 1, yeah?
Did you alternate between odd and even until you get a 1?
Okay, so
But once you get a 1, you stay with the state.
as long as I've got zeros, I'm going to jump back and forth, right? And so whenever I'm in odd, I have an odd block so far, and whenever I'm in even, I have an even number of zeros so far. It isn't until I get a 1 that I know the block ends, though. Yeah? Okay, so if I have an even block of zeros, that's not interesting, right? So I'm just going to go back to square 1. Right, now I've got my 1, so I'm waiting for the next block of zeros to start. But okay, but if I'm in odd and I get a 1, is that interesting? Yes? So I should go to a state. I need 2 1s. So far I've only got 1 1. What? Okay, so if I get another 1, this is very interesting. Yes, Marco. So if I get a 0 here, I should go where?
Sorry, when it's 1, you just loop into interesting. I don't see why we're doing very interesting. You would see 2 1s.
Well,
Oh, 2 1s, okay, yeah.
I need two ones, right? Yeah. Okay, didn't, was trying to mislead you, but I didn't succeed. Okay, so if we get a 0, then darn it, we didn't see the sequence, right? Because we needed two ones. But so we really need to start over, but this 0 could be the part of a new block, so we would want to go to odd. We don't go back here, right? Because this is what happened this here, right? We got a 0 and then 1. Okay. All right, so now I have two ones. If I'm in very interesting. Yeah.
If we get a 0 and very interesting, we go back to odd.
Okay. And then if we get a 1, we stay. So that's... Oh, okay. So far we don't have any outputs. Okay, so what should my output be? 1? Okay, now, because I am putting it in the state, this is going to happen after I clock in the two ones, right? It's not until the transition that has the second one that I will start outputting it. So I would be sitting here, let's see, I have a 0 that will take me to odd, and then this 1 will take me to interesting, and then this second one will take me to very interesting, and then here will be sitting in state very interesting, outputting the 1. Okay. How about the other states? They have outputs too, right?
0.
Everybody else outputs 0. Okay? Any questions on this? Okay, so these keywords after, very important. I don't suppose you want to do another one. Yes? No?
If you want to do another one.
Sure.
Yeah.
Okay, let's do another one. All right. Or you want to do this one on your own first? You want me to play the Jeopardy music? No.
Yeah.
Yes?
We should have a community state machine making in class playlist. That sounds like a terrible idea.
Can you put the paper down?
Oh, sorry. That helps. Okay, this one doesn't object to the beginning, I think. So you could have two 1s and then two 0s and output a 1.
I don't see this particular input in the examples, so as a matter of curiosity, if you were to say have the pattern 11001100, would that be two like
No,
strings of
no, because the 1s have to be the first.
Yeah, but if you had the 1100
Yeah.
followed immediately by another 1100.
Yeah, that would be
all
2.
be-
Yeah.
Okay.
I guess I could do it now, right? Okay, you ready? Yeah, all right. All right. So, all right. What should we do at the very beginning? Yes.
You get a 1, you go to the odd state, and you output a 1 on the odd.
Really? But I need an even length block of ones followed by an even.
Misread the beginning.
So zeros, since I first have to have a block of ones, any zeros at the beginning are useless, right? So nothing's going to happen. Okay, but if I get a 1, we'll call this odd 1. And I think we're going to do, something similar. Even 1. We'll bounce back and forth. Okay, what happens if I get a 0? Yeah.
You go to another odd even setup.
Okay. So we'll call this odd 0. We'll call this even 0. And we will bounce back and forth.
Wait, we're looking for a pattern with an even number of ones and an even number of zeros, right?
Or an odd number, an even length block of ones followed by an even length block of zeros, or an odd length block of ones followed by an odd length block of zeros.
Oh.
So it could be first you get odd ones and then odd zeros, or you get even ones and even zeros. Okay, so we're probably going to.
States quite a lot.
All right.
Could you simplify this by making it 2 state machines?
No, that's not simpler. Yes.
If even 1 got a 0, would it also go to odd 0?
Well, I could, but if I do that, I'm not going to remember whether I'm looking for an even block length of zeros or an odd length of zeros, right?
That's the same thing for odd 1.
Yeah, so I kind of need to keep track here, right? So I could do this. Okay. What do I do with ones? Suppose I'm here and I get a 1. Let's see, is this whenever? Okay, so let's see, so we had 2 1s, 2 zeros. Looks like we only output the 1 after this block. So we get a 1 here. So, okay, so 2 1s, 2 zeros would be here. So we get a 1. We want to output a 1 directly, but I think I want to go back to odd 1, right? Because that's the first one. So I want to output a 1 here. Okay, and now I have 2 zeros. I have a 0, 1. So, okay, no, that was, okay, now I have a 1 and a 0. Ooh, and another 1. So this was an odd 1 followed by an odd 0. So again, if I get a 1, I'm going to go back here and output a 1. Right, so if I'm in here and I get a 1, that's time to leave this and go back to here, because now I got a 1 and a new block is starting. But notice, these are still very similar. What if I were to just go, instead of going from here to here, I'm just going to go here. Wouldn't that work? I just kind of reverse the parity. Okay, so you don't have to do this, but if we were to run Moore's algorithm to minimize states, you would discover that in fact these two are equivalent and these two are equivalent. Okay, all the other outputs have 0. And this is a Moore machine, I'm sorry, a Mealy machine. Okay. Yes.
The output 0, but the right out 0 and the left uses 0. They both have to point back to odd 1 if they are 1.
Yes. So these will all go back to 1, but they're going to output 0. Right? As soon as we're down here and we get a 1, that's the block of zeros are over, and we've got a single 1, so they take us to odd 1. But whether the output is 1 or 0 depends on where we were. Okay, I think it's time to go. What?
I said already.
Already. I know.